Hey there, physics fans. Today we are going to talk about course problem 10-1. So course problems are special problems that we feel get after some additional concepts. So this first one is a multi-concept problem dealing with conservation of energy and conservation of linear momentum. So the key words you're going to take away from that problem statement are that you're looking at mass 1, which is released from rest, and it's above mass 2. It starts on a frictionless ramp. And then that there's going to be a completely inelastic collision between mass 1 and mass 2. So your task in the problem is to actually calculate mass 2. And knowing that we're dealing with a collision, you might think, oh, this is a conservation of linear momentum problem. But remember, in order to solve conservation of linear momentum problems, you need to know all the masses and all the velocities, or those are one of the variables you're looking for. In this case, in order for there to be a collision, mass 1 has to have velocity before it strikes mass 2. Unfortunately, we don't know initially what that velocity is of mass 1. Therefore, before you can solve for mass 2, you've got to solve for that velocity from mass 1. And that's why you have to do conservation of energy before you can solve the rest of the problem. So going into that draw step, I took the drawing from your picture, but I added a coordinate axis so I can label and identify what's x and what's y. I notated the initial position for mass 1, because we need to know that for conservation of energy. And I notated the final position for mass 1, because again, we need to notate that for conservation of energy. Given mass 1, the height, and then the final velocity of them combined, the last thing is, of course, our assumptions. It's a closed and isolated system during the collision. That's how we're able to utilize conservation of linear momentum. So for this video, I'm going to start out with the conservation of energy portion, solving the problem, and then we'll go into conservation of linear momentum. All right, so first, our conservation of energy. Now that we have a really good picture, we always do our conservation of energy table. So in our table, we utilize that equation from the PRC that the work due to non-conservative forces is equal to the change in energy, or the energy final minus the energy initial, which I'm listing here. All right, so energy final minus energy initial. When I say final, I mean the energy final at this position here right before mass 1 collides with mass 2. And then when I say energy initial, I mean right up here where what's the energy of the system where mass 1 has not left yet, before it's released from rest. Now in the table, you go straight down through your PRC, where you know you've got kinetic translational energy, kinetic rotational energy, gravitational potential energy, and then elastic potential energy. So when I go through this table, I'm going to look at my picture. I'm going to say, in the initial position, do I have kinetic translational energy? And the answer to that question is no. Mass 1 has not started moving. Block 1 has not moved. Now at the final position, mass 1 is moving. So yes, there is going to be kinetic translational energy. 1/2 mv squared. 1/2 times the mass times the speed squared. Now I look at kinetic rotational energy. Is the object rotating? Well, not at this point. We will get to those problems in the future, and we will discuss all about kinetic rotational energy. And then I look at gravitational potential energy. In the initial position, is there gravitational potential energy? The answer to that question is absolutely yes. According to my reference point, if I state that this at the bottom is where gravitational potential energy is equal to 0, then at the top there must be gravitational potential energy for mass 1. At the final position though, right before mass 1 collides with mass 2, there is no gravitational potential energy. And that's why that draw step is so important to filling in our conservation of energy table. And then lastly, is there a spring in the system? When we look at elastic potential energy, we're looking for any sort of spring. And there is none in this picture. So for this case, for this particular problem, there's no elastic potential energy. Now I'm going to finish off the table, and I'm going to solve for this speed right here, the speed of mass 1 right before it collides with mass 2. So I have my work due to non-conservative forces is equal to 1/2 times mass 1 times speed of mass 1 squared minus mass 1 times acceleration due to gravity times that change, that height for the gravitational potential energy, that h. So now I'm going to solve for this v. I do know that there is no work being done by non-conservative forces. In this case, there's no drag and there is no friction. This is a frictionless ramp. It's told to us into the problem. So I can say that the work done by non-conservative forces is equal to 0. So I'm going to do a quick algebraic solve, or 1/2 times the mass 1 times that speed 1 squared is equal to mass 1 times acceleration due to gravity times the h. Mass 1's actually cancel, so the speed is equal to the square root of 2 times the acceleration due to gravity times that h, that distance here. So now I've solved for the speed of mass 1 right before the collision. Fantastic. Now I'm going to go into doing the conservation linear momentum problem portion of this problem. Given this speed, given the other variables, we can now easily solve for mass 2. So I'm going to go and do that over here. When we're looking at conservation of linear momentum problems, we always draw a just before and a just after picture. This one is a pretty simple picture. Mass 1 has a velocity, and it's going in the positive x direction. Mass 2 does not have an initial velocity. Yay, that makes it super easy. So I'm going to label this picture just before. And then I'm going to label a just after picture. We're given in the problem that it's a completely inelastic collision and that they have a combined velocity. So in my just after picture, I'm going to have mass 1 connected to mass 2. Meaning they have a combined mass. And they continue to move together with a combined velocity. So our conservational linear momentum equation is that the summation of the initial linear momentum, which is a vector, is going to be equal to the summation of the linear momentum in the final position, which is also a vector. So all the initial linear momentums, you add them all together. All the final linear momentums, you add them all together. And it's a vector. So that means I should resolve this out into the x and the y. Fortunately, though, with this problem, velocity is only going in the x direction. We see that here with our picture. We see it up here with our drawing. In this case, there is no velocity going in the y direction. So that makes it a little bit of an easier conservation linear momentum problem. But I'm still going to rewrite my linear momentum equation so that the linear momentum initial in the x direction is equal to that summation of the linear momentum in the final position in the x direction, just to be very specific. Now I'm going to go through this step here. I have mass 1. It's time that velocity in the x direction, which is essentially the magnitude, the speed that we calculated here. And that's going to be plus mass 2 times that initial speed of mass 2, which we know to be 0. And all that's going to be equal to the combined mass, mass 1 plus mass 2, times their total velocity in the x direction, which is that magnitude which is provided at the beginning of the problem, in the x direction for their velocity. So now I'm looking for this variable here, this mass 2. This is what I'm solving for. So it's a couple algebra steps. And simplify that. And then just going to take this velocity total, the combined velocity total in the x direction. I'm going to bring it over here. So now I have mass 1, v1, I'm going to divide And one final step. Mass 2 is equal to all right, so the final step we're going to do is we're going to substitute in this value right here over into this equation. So I have mass 2 is equal to mass 1 square root 2 times acceleration due to gravity times that h value. All that's going to be divided by the speed, the magnitude of the total velocity minus mass 1. So our next step is to do the check step, of course. In the solution, it's mass 2 is equal to 11.5 kilograms, which is greater than mass 1. So when we go through our check step, we always check those units in sig figs. So 11.5 kilograms, that's 3 sig figs, just like the problem is provided. So that'll check out just fine. And then, we look, does it make sense? And it does make sense. Mass 2 is greater than mass 1. Given their decrease, given that decrease from mass 1's initial velocity just before the collision to their combined velocity after the collision, it does make sense that mass 2 would be so much greater than mass 1. So thanks so much, physics fans. Good luck. Keep charging on, and we'll see you next time.